We're looking at diversification. Last time we looked at diversification for if we had uncorrelated assets. Today let's look at diversification if we have positively correlated assets. Let's just see where we have here. Suppose here. So we're still on portfolio theory, but we're considering diversification. Okay, we saw that what happened for uncorrelated assets i.e. Sigma ij equals rho ij equals 0 for all I not equal to j. Okay. So these are totally uncorrelated. The correlation coefficient is 0, and also the covariance is 0. We showed that the limit as n approaches infinity of our portfolio variance equals 0. Remember, we had that 1 over n term there. Let's see. So that was really easy to show, because the second term dropped out on the right-hand side, the one with the covariances. Now, let's look at positively correlated assets. And here we're going to have rho ij. It's going to be strictly less than 1. We don't want them to be perfectly positive correlated, but we want them to be somewhat positively correlated here. And this is true for all. And sometimes I use the following mathematical shorthand. We use looks like an upside down A, I not equal to j. Okay. Recall that our expression for the variance equals, we have two terms on the right-hand side. I equals 1 to n, wi squared, sigma I squared. These are for when I equals j. So this is the case when I equals j. Let's see how we do here. When I equals j, remember that the covariance becomes the variance here. Then we have the terms where I does not equal j, plus the double summation I equals 1 to n j equals 1 to n. And we want this all over I not equal to j. So the second term on the right-hand side are all the covariance terms. And they are wi, wj, rho ij. Let's do the rho ij. Oh, let's just do sigma ij. Sigma ij. Okay. Now, what do we get here? We know that we have that wi equals 1 over n. We assumed, for simplicity, that wi equals 1 over n for each of the assets, each of the n assets. So we have an equal amount of our budget in each of the assets. Okay. So now we get what? We get sigma p squared. The portfolio variance equals what? We have wi squared. So this is the sum of 1 over n squared. I equals 1 to n. Sigma I squared. Okay. Plus, we have this double summation for the I not equal to j. I equals 1 to n. J equals 1 to n. And I is not equal to j. Okay, let me move that up with just a itsy bitsy. Here, so again we have 1 over n squared because wi is equal to 1 over n, wj is equal to 1 over n here. So we have that 1 over n squared sigma ij. Okay. Now, what do we want to do? We're going to do a trick here. We're going to simplify this. By factoring 1 over n from the first term on the right-hand side. And n minus 1 over n from the second term on let's just do it on the right-hand side. Okay, so let's see what we get. And we'll see this. This is also nice. So what do we get? We get this resulting in the following. The portfolio risk or variance here is what? Equals 1 over n, and the summation I equals 1 to n, sigma I squared over n. Okay. Plus what? Plus n minus 1 over n times the double summation I equals 1 to n, j equals 1 to n, to n, sigma ij, n times n minus 1. Okay. Now, notice, why don't we do this first? We could have also said the following. Yeah, let's do this. That n minus 1 over n times 1 over n times n minus 1 equals 1 over n squared. Okay, because these just cross off. So that's how we do this trick on the right-hand side, the second term. Okay. And the total number of terms on the right-hand side is what? First, we have n terms for when I equals j. N, these are for when I equals j. Then we have plus n times n minus 1 terms for I not equal to j. I not equal to j. And why is that? We have that for I because we have n i's and n minus 1 j's not equal to I. So for each I, there are n minus 1 j's that are not equal to it, because the total number is n. So what do we get here? This equals n plus n squared minus n. So these two cancel out, equals n squared. So that's a check. We should have n squared terms on the right-hand side. Okay. Now, let's go on. This is a nice derivation here. So let's look at that second term. On the right-hand side is the sum I equals 1 to n. Let me make sure I wrote that here. This should be I not equal to j here. Good. J equals 1 to n. I not equal to j equals let me get this. I not equal to j of sigma ij. Let's not do this. Sigma ij over n times n minus 1. Now, let's look at this again. So here are the covariance terms that are positive, and underneath we have n times n minus 1. We have n i's and n minus 1, like we said before, j's not equal to I. So for each I, there are n minus 1 guys here. So n times n minus 1 is minus 1 equals the number of covariance terms. So what is that right-hand side? So the sum, the ij over n times n minus 1, and if we sum this, let's just sum this over all I not equal to j, equals sigma ij times n minus 1 equals sigma bar ij equals the average covariance. And this again is I not equal to j. Okay, so the second term turns out to be the average covariance. So let's look at both terms together. So we have the following. Let's get these two terms together. It's easy. This positively correlated is just a little bit more difficult than the uncorrelated. So we have, that doesn't look too good. Let's write that out better. The following. The portfolio variance is equal to what? Equals 1 over n times sigma bar squared. So the first term turns out to be what? It turns out to be the average, 1 over n times the average variance, plus n minus 1 over n times sigma bar ij. So that's the average covariance there. Okay. So what does this equal? This equals 1 over n times sigma squared bar, the average variance, plus 1 minus 1 over n times sigma bar ij, which is the average covariance. So the limit as n goes to infinity, but the number of stocks in our portfolio go to infinity, equals what? Equals the limit as n goes to infinity of this term, 1 over n sigma bar squared plus 1 minus 1 over n sigma bar ij. Okay. So if the n goes to infinity, this goes to 0. Okay. And this goes to 0. These two terms go to 0 in the limit. So what are we left with? And the limit as n goes to infinity of sigma squared p equals what? Equals 0 0 is our variance. This is 0, so this is plus sigma bar ij equals the average covariance. So when we have positively correlated assets, we can reduce risk, but we can only reduce risk to the average covariance here. Leuenberger gives an example with numbers, but it's just as easy to do it without numbers. Okay, let's do this. Text. So graphically, and that figure has specific variance and standard deviation, but for any variance and standard deviation, we can get the following. On a vertical scale, let's put the portfolio variance. And on the horizontal scale, let's put N, the number of assets in our portfolio. And what happens here is we get something that looks like this. And this is our average sigma bar ij. That's our average covariance. So we can only reduce risk to the average covariance. This, of course, on top is the diversifiable risk. Okay, that's our diversifiable risk. On the bottom is the undiversifiable risk, or the market risk. We could call this let's come down here, undiversifiable. Sometimes called the market or systemic risk. So we're going to see one of the main results is that of diversification is that you should never bear diversifiable risk. Because all you have to do is diversify that away. Now, sometimes you may not have such a big portfolio, so you'll have to bear some diversifiable risk. Why don't I say this, all diversifiable risk? That'd be a better way to say it. Okay. And we can't reduce the risk to below the average covariance. Okay. Now, this has got to be 6.1. Okay. 8. Okay. Let's look at section 6.4 of our text. And this is entitled the portfolio diagram lemma. Now, what it is just a result. It's not a lemma. A lemma is something that is a result that's used to prove another result. This is not used to prove another result. So I don't know why they call it the portfolio diagram lemma. And it's for two assets, 1 and 2. Okay, so those are our assets. And it looks like the following. We're going to plot R bar on the vertical axis, and we're going to plot sigma on the horizontal axis. This is like we usually do. Now what happens here is it goes the following. That we have something like this. Then it goes down to something like this. Then it goes to something like this. Okay, so let's look at this. So we have this triangle here. And let's do some points. Let's call this point 1. Text calls it 2. But I'm going to use 1. And I think you'll see why. 1 is the highest. Then 2 is this one. So this is the, what is this? This is the risk and reward for expected reward for asset 1. This is for asset 2. Now, let's draw a line in here. Okay. Now let's look at the legs of this triangle. This leg of the triangle corresponds to row 1, 2 equals -1. This leg of the triangle also corresponds to row 1, 2 equals -1. Okay, so that looks a little strange. We have two legs of the triangle corresponding to perfectly negatively correlated assets 1 and 2. This leg is row 1, 2 equals +1. And somewhere in the middle here we have this other guy that corresponds to row 1, 2 equals to 1/2. Okay? I should have bent it out a little more. Okay, that's good. Now what does this mean here? And we're going to call this point here A. This third vertex, A. So let's see what this means. And why don't we write this down here? No, let's write it here. Where the zero risk portfolio of assets 1 and 2 has an expected return R bar equals R bar 1 sigma 1 plus R bar 2 sigma 2. Let's make sure that's right. No, this is definitely not right. Let's see something here. Hold on for just a second. I want to get this, make sure I get this right here. This should be R bar 1 sigma 2 plus R bar 2 sigma 1 all over sigma 1 plus sigma 2. So this is R bar 1 sigma 2 plus R bar 2 sigma 1 over sigma 1 plus sigma 2. Okay. And we did calculate that. Okay, here we go. Good. Yes, this is exactly right. Excuse me, I had a mistake in my notes. I just corrected. Okay, so any combination of assets 1 and 2, we should say any non-negative combination, so no shorting, of those two assets must lie within the triangle. Okay, so any combination of those must lie within the triangle. If we allow shorting, we can extend some of the legs. Let's see that. Shorting, we would get something that looked like the following. R bar, sigma, this is R bar P and sigma P, of course. And we would get something that looked like this. We get 1, 2, A, as before, as the three vertices. And now, if you allow shorting, what happens? This would continue to go up this way. This would be shorting asset 2. Why? Because it goes up from the 1, we're buying more than 1 here. So we're short. To do that, we must short asset 2. And here, we short asset 1. So now you see a nice thing. It would never pay for us to short the better of the two assets, because we would get less and less expected rate of return. But we would still increase our portfolio variance. Now, if we short the riskier asset, then we can get a higher expected rate of return, but at the cost of a higher portfolio risk. Okay. So that's what happens if we short. Well, let's forget about the short for now. Now, we'll do that tomorrow. Instead of proving this result, this lemma, we will do a numerical example Okay. Now, the numerical example doesn't constitute a proof of the lemma, but we'll see what happens in the numerical example is exactly what we expect to happen from the lemma. Now, let's consider two assets, 1 and 2. And for those, we have, let's suppose we have the following data, that the expected rate of return and the standard deviation are as follows. For the first asset, we have an expected rate of return of 14 and a standard deviation of 6. Okay, here. And for the second asset, we have a rate of return of 6, and a standard deviation of 3 here. Okay, so we have these two. So let's graph these two. This is easy. We're going to graph sigma 1, r bar 1, and sigma 2, r bar 2. Remember that I'm using a little bit different notation. I take 1 to be the one with the highest return here. We graph these two guys. We get the following. Some bad notes here. Somehow I didn't bring the right notes here. Well, let's just graph these. Okay. This is sigma I, and this is r bar I. Okay, so the first guy has what? The first guy is 14.6, right? The first guy. So it has 14, so let's say 5, 10, 15. So it's 14, and it goes out 6. And this, say this is 5. So 14.6 is about here, actually 6.14. So this is 1. This is 6.14. And for 2, we have what? The r bar is 6, and this is this is 3. So now we get something that look like here. This is 2. And here we have what? We have 3, 6. So this is the one leg of the triangle. Now the other leg, we're going to see, hits right on 10. Okay. Okay. So we had. Let's calculate A. A. We said that A equals r bar 1 sigma 2 plus r bar 2 sigma 1 over sigma 1 plus sigma 2. 2. Okay. Now, what do we get for that? Let's calculate that. We get that A equals the following. R bar 1, sigma 2 is 3, plus R bar 2, which is 6. Sigma 1 is R bar 1 is 14. Sigma 2 is 3. That's right. R bar 2 is 6. And sigma 1 is 6 here. Okay. Let me make sure I have the right data here. I think I have the wrong data for some reason. Yeah, this data is wrong. This should be 8. Let that be 8. I thought that was wrong. This is 8. So this equals 14 times 3 plus 8 times 6. Okay, over what? Sigma 1 plus sigma 2. Sigma 1 plus sigma 2 is nothing more than 3 plus 6. 6. So let's look at that. So 14 times 3 is 42. 8 times 6 is 48. And now what we have is the following. We have this over 9. So this equals 90 over 9 equals 10. So the expected rate of return for a zero risk portfolio of 1 and 2 equals 10, and typically we have that in percentage. Okay, which is a pretty damn good rate of return if you could get that now. Okay. So let's graph this again on the correct way. So graphically, we have the following. And this graph this will be a better graph because we didn't use 6 here. It's R bar, sigma here. So we have what? We have 8, 14. So let's go 5, 10, 15, 5. So we have 8, we have 6, 14. So 6 here, and then 14 there. So this is 1. 2 is what? Goes up 8 and over 3. So this is right here. 2. Here's one leg. We said that A equals 10, so here's another leg, and here we go here. So this is our portfolio diagram. All non-negative combinations of 1 and 2 must lie within that triangle here. A 1 equals 614. 2 equals 3, 8. Okay. Okay, good. Now, let's see about this portfolio diagram lemma. Okay, let's first consider the case of row 1, 2 equal plus 1. It's a perfectly positively correlated assets, 1 and 2. And let's do some calculations for that. So we know, what do we know? That R bar P equals W1 R bar 1 plus W2 R bar 2 equals W1 R bar 1 plus 1 minus W1 R bar 2. Okay, so it's linear and W1. And it doesn't depend on row 1, 2. So it doesn't depend on the relationship between 1 and 2, because all you have are the weights for 1 and the expected values. Okay. So it's going to be the same for any row 1, 2. Let's write that down. Any value of row 1, 2. Okay, so we only have to calculate that guy once. Now let's look at sigma p. Sigma p equals the portfolio standard deviation equals the following. Equals W1 squared sigma 1 squared plus W2 squared sigma 2 squared plus 2W1 W2 sigma 1 2. Sigma 1 2. Okay, and we take the square root of all this because we're talking about the portfolio standard deviation here. So it equals W1 squared sigma 1 squared plus 1 minus W1 squared sigma 2 squared plus 2W1 1 minus W1 sigma 1 2, and we take the square root of that. Let's move this over a little bit. Okay, good. Okay, now clearly this is going to depend on the correlation coefficient. Why? Because we can express this as what? Rho 1 2 sigma 1 sigma 2 from the definition of a correlation coefficient. So first let's give a let's summarize our calculations for this case. For rho 1 2 equals plus 1. So we're going to look at that leg for the perfectly positively correlated. So what we're going to do is we're going to vary W1, then we're going to calculate the rate of return, and then we'll calculate the standard deviation. And we're going to do this for the following W1s. We'll let W1 go 0, 0.2, 0.4, 0.6, 0.8, and 1.0. So if W1 equals 1.0, what does that show? If W1 equals 1.0, we're at 1, right? Okay, because all our weight is on asset 1. And W1 equals 0, we're at 2. Okay, we're at asset 2. So we can fill these two out real easy. This is 8.3, and this is 14.6. Okay, let me look at our other numbers here. The numbers I'm getting are the following. The rate of return is linear in W1. So it goes 9.2, 10.4. It goes up, for every 0.2, it goes up 1.2. 11.6, 12.8, and then it should be 14, right? Yes, exactly right. Okay, now, the standard deviation goes as follows. 3, 3.6, 4.2, 4.8, 5.4, 6. Now you can see that this is linear, but the standard deviation is not linear. This is linear in W1, not linear in W1. Because as we go from 0 to 0.2, we go up 0.6 here. That is linear in W1. This is also linear in W1, 0.6, 0.6, 0.6, 0.6. Okay. Well, sigma, both the expected rate of return and the standard deviation of the portfolio are linear. Okay, thank you. I think we're out of time here. I'll go over this again. How you doing, my friend?